Welcome. We're going to talk about combinatorics this week. Specifically, I want to talk about counting, which should be a review concept for all of you from your discrete math. Now, I will simply start by saying a couple things about this. Combinatorics is what got me interested in cryptography in the first place. I remember taking a combinatorics class as an undergrad. Not that the secrets and encryption were already really cool, but talking about the different ways to do things, all the possible options, and so forth. That becomes a kind of a critical idea here. So I want to go through this and I want to do some problems. And I'm expecting that all of this should feel like review. I'm also going to make a comment real quick that I expect you to actually not just rely on formulas, but really think about how to break them apart. Because as we attack bigger and bigger, nastier problems, formulas fail us, and then we have to use our thought process about how to get this. So we're going to go ahead and do a counting process. And I'm gonna give you problems. I'm gonna pause. I want you to pause the video and I want you to work through it. And then I want you to come back. So let's just jump into it. Let's do a couple problems. So our first problem is a classic one. It deals with an ancient papyrus that was actually found in Egypt that had some math problems on it. And one of them is this: there are 7 houses. In each house, there are 7 cats. In each cat kills 7 mice. Each mouse has eaten 7 spelt seeds, and each spelt seed has produced 7 hectares of spelt. What is the sum of all the named items? Well, to do this, what we're really going to have to ask is, let's break it down. I'm going to need to ask the number of houses plus the number of cats plus the number of mice plus the number of spelt seeds plus the number of hectares of spelt. That might be Hecat. I don't know if any of you know how to pronounce any of those words. I don't, but this is a classic one. So the question is, how do I do it? Well, some of these things are really easy. Houses, as we read simply from this, is just 7. We're going to add each of these together because they're separate situations. Cats, well, for each house, there were 7 cats, which means there's going to be 7 times 7. Or instead of writing that, I can simply write 7 squared. For mice, there would be 7 cubed because there's 7 mice per each cat. So we multiply it again by 7. Spelt and hectares would similarly be 7 to the 4th and 7 to the 5th. And then I simply need to add up all these numbers. Again, quick reminder, you do not need to actually do the computations and pull all these all the way out. I want you to write out something like this and understand how they word versus working on understanding other things. Also, as we go further on, please do not use PNK or CNK notation. That notation, honestly, is not used in any of the cryptography books I've found. It's only found in like super basic discrete math books, and even then, it's not even in most of them. It's in about a third of them, and or in a very elementary statistics. Advanced statistics doesn't use it either. So this, because P is for probability. And what does C mean? Well, there's lots of things of what CNK could be or PNK. So for that reason, we do not usually use that notation. So do not use it in this class. Use the actual notation as you see me use. All right, with that said, let's move on to our next problem. So we've talked about cats. Yay, let's move to something else. Let's talk bit strings for a second. So we want to find out how many different bit strings of length 7 are there. All right, I want you to pause the video and figure this one out. All right, so if you did this, you could do this a couple ways. One, you could literally brute force this thing. I would not recommend that. Another one is just let's just look at it. So I have 7 bits possible. The first one has 2 options in it because it can be 0 or 1. The second one bit can have 2 options in it, again, a sec, and so forth and so on. Now the question comes, do I multiply or do I add these together? The answer is I'm going to multiply these together. Like so. In that case, I get 2 to the 7th power. If you really want, this is 128. I personally know my power is a 2, up to, well, I think it's 10th. But you don't need to do this. You don't need to figure out 128. If you want to just leave it as 2 to the 7th, I would highly recommend that, because we're going to deal with things that are much larger. And if you get like 2 to the 100th power, now we're talking a very large number. Yeah, you don't really want to start messing in that realm. All right, so that's what we do. But what if we take the same problem and we just add a slight variance? What if I add this restriction that there are 3 ones in there? Now, just a quick thought process on this. Question before you answer it, and I want you to think about this. Should this number be bigger, less than, or possibly equal to 128 we just got in the previous answer, this 2 to the 7th power? Think about that, as well as attempt to solve it and then come back. All right, so hopefully you thought about that. You paused your video and now you're unpausing it, etc. I'm going to go on. This number, what we know is that this should be less than 128, or 2 to the 7th. Why? Because we're putting a restriction on it. All of these were obviously counted in the general case. Now, if I say there have to be 3 ones, now it gets a little bit trickier, because where are the 3 ones is the question. So really just think about this. I could have put all 3 in the front, and obviously there's only one way to do that. But what if I do 2 in the front, and then I go 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, and I keep doing this, and you'll notice I have 5 cases here that I just quickly made up right there. So we have 5 situations where I have 2 ones in front. There's still more ways to have done this, a lot more ways. What if I had 1 1 and then the other 2 twos were I had put a single 1 in the beginning and the other ones are all mixed up? What if we put a 0? So we have these problems. So instead, our question really is, let's instead look at it this way. I have 7 things, 7 spots, and I'm going to pick 3. So suppose I pick this one, and this one. So the question then is, how many ways can I choose 3 things out of 7? The answer is 7 choose 3, or the binomial coefficient, which, a quick reminder, is 7 factorial over 7 minus 3 factorial times 3 factorial, which is going to be 7 times 6 times 5 over 3 times 2 times 1, because this is 4 factorial, so it gets rid of the rest of the 7 factorial. And that 3 times 2 times 1 is equal to 6. So this is just 7 times 5, or 35. But again, you could just write this and understand that that's the answer for this particular situation. Again, don't be reliant on the formula. Understand that why that works in this particular situation and how it incorporates. Now, let's look at another example that's a little bit different. Again, we'll kind of continue this idea of some basic combinations. So we're going to create what we call words. Truth is, when I say words, a word is simply a string of characters. So you could call these, how many different strings can I form from the characters capital A, capital B, capital C? If you want to do it from a computer science term. So words is typically used, a cryptographic term, and also in combinatorics to refer to a string of characters of some sort. And then the characters from which we draw is called our alphabet, because that's actually how the alphabet works, is we have a list of characters we use and we create words using them. Some are nonsensical, but some are actually value. So let's just talk about this one. How many ways can we do it? Now, we could literally brute force this, because this is really easy, and I could go A, B, C, A, C, B, if A is in the front, and then I can do B, and it's gonna have 2 situations where B is in front, and C will similarly have 2 situations where it's in the front. And so we end up with 6 words. Boom. That's nice. But why? Well, let's think about it in terms of our words. Our words obviously has to use 3 characters. I had 3 options to put in the first spot because I could have picked A, B, and C. But once I picked that, if I'm just using these 3 symbols and mixing them up, then I would have 2 in the second spot and 1 in the last spot. This would be if I have to use all 3 of these characters. And that's obviously 3 times 2 times 1, or 3 factorial, which, by the way, happens to equal 6. So that's actually how we got the answer in a more general way, is just taking this and kind of breaking it apart. On the other hand, if I was to simply state this a little bit differently, I could just say how many words can I form where these are used in any order, and repetition is allowed. If I'm doing that, then we have a massive problem, because if I'm allowing this to be more general, how many different words could be formed? Well, if I'm allowing repetition, then I could have just had word of length 1, word of length 2, word of length 3, and that's just infinite number of options, and that's just not really cool. So I'm going to stick with this option. But again, let's just do a modification of our problem. What if I add a 4th symbol, but it's a repetition of A? Now how many options? All right, go ahead and pause the video and answer this question. All right, so suppose you did this. Let's look at what our options were. Again, you could try to brute force this. I would not recommend it. These numbers grow quickly. And as a reminder, brute force is not actually something we ever encourage in cryptography. In fact, even going back to the beginning of the class, I'm going to go off on a side note real quickly. We talked about permutations. So if I took the letters A, B, C to Z, and I was assigning them the numbers 0, 1, 2, 25, we talked about doing shifts, but shifts are simple. But what if I simply did a random mixture? So A goes to 2, B goes to 1, C goes to 25, Z goes to let's go 13, and we just have all this giant mixture. How many different mixtures are there? Since A would have 26 options, there'd be 26 times 25 times 24 times 1, or 26 factorial. And real quickly, to help you all understand, even if you were running a highly efficient computer, to run through all 26 factorial possible options on a message would take you years. It's not viable. So it's not something that we even do for 26 factorial. We're going to deal with things that are much bigger than 26 factorial. So we have to talk about how do we do these things more appropriately. So in this one, we're again going to use factorials. I'm not going to brute force this because this one's going to get ugly, but I'm just going to look at a situation for a second. So what if I called this A1 and A2? So they're more distinct. Now, if I have my 4 letters, I have 4 different options to put in the first one, 3 different options to put in the second one, and 2 options and 1. And so this would be 4 factorial. And we'd be like, yay, we're done. But there's a slight problem. Using this, I could have come up with the word A1, A2, B, C as one word, and then A2, A1, B, C as another word. So see, this 4 factorial counts both, which means it's counting a repeated, because to the naked eye, they would see these things. The computer, all it would see is this. It wouldn't see the subscripts. And so it's going to be like, those are the same. And so we would just double count it. But that's going to happen for every single combination of A's. We could have, that the A's were in the same exact spots, but just transposed. So what we have to do is actually take this 4 factorial and divide it by 2 factorial, which is the number of ways to have mixed up our 2 A's. This only is true because I have 2 A's in here. So I get this 4 factorial over 2 factorial, which is just going to be 4 times 3, or 12. Again, you can leave it here in the giant factorial form, or you can multiply it out if you really want. But again, our numbers are going to get big fast. And if you give me the answers, I want to see the factorial so I see where you're getting that from and not just trying to brute force it. That's going to be very dangerous. Let's keep on talking about passwords. So let's talk about what if I'm trying to figure out how many passwords are possible with uppercase letters or a digit? And then, but the length of the passwords could be 6, 7, and 8. Because a minimum length of 6 and maximum length of 8. Go ahead and pause the video and try to do this. And just think about for a second about what that answer would be. All right, so let's talk first about what is our quote unquote alphabet. Our alphabet's going to have uppercase letters, which there are 26 of those, and it's going to take a digit 0 through 9, which is 10 of those. So we're going to have 36 characters that we're going to be picking from. So I'm going to have to deal with passwords of length 6, length 7, length 8. And just to show this, I'm going to do the one for 6, and then we'll deal with all the others in a second. Well, in 6, I would have 36 options for the first character, 36 for the second character, 36, 36, 36, and 36. So that would actually mean there are 36 the sixth powers. Well, using that intuition then, if I had 7, it would just be 36 to the 7th power, and 8 would be 36 to the 8th power. The question is then, what do I do with these different situations? Do I multiply them or do I add them? In this case, we're going to add them because they're totally unique to each other. Because the number of length 6 cases, if I pick password length 6, then obviously I can't have password length 7. So that's completely separate and they're completely independent of each other, and we might as well just add them in those situations like this. So we're just counting different situations that could have occurred. And again, the goal here is simply to leverage all these concepts to our advantage. All right, so that's of length 6. Now, let's do a similar problem. What if I have 100 students that are eligible for an award, and the winner gets to choose among 5 different possible prizes? How many outcomes are there? All right, go ahead and pause the video and answer this question. All right, so hopefully you did that. And hopefully, I mean, the answer should be, if you think about it, I'm gonna have students, and my students are gonna have 100. And then I'm gonna have prizes. And each student is gonna have a choice of 5 prizes. Since each student can choose 5 prizes, we're gonna have 500 total options. 100 times 5. Okay, this may seem really simple, but what if I just change the problem ever so slightly? Now this becomes a whole lot harder. Because now I'm going to add in first, second place, and third place. Same as before. So I still have 100 students. Each of them gets to choose one of the 5 prizes, but there's only one of each prize, which means once that prize is chosen, it's gone. All right, so this becomes, and there are 5 unique prizes. That's kind of important. If some of the prizes were repeated, then it makes the different combinations not quite as plentiful. So let's just look at this in terms of how you would deal with it. Actually, I didn't give you a chance to pause. Pause and do this yourself, and then I'll do it. All right, so if I'm doing this, I'm going to break this into 3 situations, actually. First place, second place, and third place. So first place, I have 100 possible students I can choose, and they get to choose from 5 prizes. We already dealt with this situation. It was the previous problem. But second place, let's go to second place. Second place would have, since I've already picked one student for the first place, there's only 99 students that are left. Similarly, there's only 4 prizes for each of them to choose from because one of the prizes has already been chosen. So notice that each of these scenarios is based on what happened in the first place scenario. Similarly, third place would be 98 times 3 because I'd only have 98 students left to choose third place and 3 students left to choose, 3 prizes left. But the question is, what do I do between these 3 values? Do I add them? Do I multiply them? we're going to multiply, because if you think about it, each one of these scenarios has, this scenario also has one of these possible 99 times 4 possibilities for second one. So you pick your first one that's fixed, and now I'm going to go to my second one. So because they're splitting out from each of them, if you draw a decision tree or something like that, that's kind of look like. So we're going to get 100 times 99 times 98 times 5 times 4 times 3. And sometimes you'll see something like this. It'll be 100 factorial over 97 factorial times, and this is going to be 5 factorial over 2 factorial, because I'm just dropping off the last couple of terms. And I could write it down here in this form. I could write it like this. Both are very viable options, and we're still good. All right, let's go to our next one. What if we change it just a little bit? Now let's talk about permutations. Now, again, permutations, if you watch your book, and this is common, permutations are often actually, the permutation function is pi of n, meaning it's going to take, this is where n is assigned in the permutation pi. So normally a permutation is mixing up numbers. So I have 1, 2, 3 to n. And then down here I have 1, 2, 3 to n. Each value goes to exactly 1. So that 1 has n values, 2 has n minus 1 values, 3 has n minus 2 values, because it can't, its choices are based on what the previous ones were. So if we're just counting the number of total possible values, permutations, if no restrictions, we would get n factorial. Okay, so that is the number of ways to do it where there's no restrictions. But we have a restriction in here. And that's what we want to leave at least one number fixed. Well, there's lots of different ways. A classic one, and the key word in here that I'm again going to just kind of point out to you, is at least one. Why is that so important? Well, at least one means there's one or there's more. So we have two different ways to attack this. One is that we can take n factorial minus all the situations that are not good, which means all the situations where no number is fixed. Or two, we could literally go through the situations about what if one number is fixed? What if two numbers fixed? What if three numbers fixed? And work through there. I'm going to do the latter situation because the truth is, finding how many ways there are with no restrictions is just as messy and horrible as this one. And so what this literally is going to be is I'm going to take, so let's think about our first one. At least we have, so we're going to have one number fixed. We're going to have two numbers fixed. I should say one or more fixed. So the best way to guarantee that I have at least one number fixed is to fix a number. And if I fix a number, it turns out that's just going to give me the answer right there. But it's going to do a little bit of an over count because it's going to include, it will include other situations. So let's start by choosing a number. So I'm going to choose any number. So let's choose 1. Let's suppose that 1 is fixed, which means 1 goes to 1. Well, then all the other numbers, 2 through n, 2 has n minus 1 options to still do. Then 3 would have n minus 2, because I don't care if it goes, 2 goes to 2, it just can't, we've already got 1 fixed, so we're going to have that thing done. And it turns out this one's actually going to be really easy because, so what I have is n minus 1 factorial That's what this thing is going to end up giving me. Because again, 2 can go to anything. We don't care what, we're going to range these however we want because we've already fixed the 1. Now, this is one way to have done this. The problem is I picked 1. Who says that 1 has to be the one that was picked? What if I picked 2? Well, if I had picked 2 to be the number that had been fixed, then I could again get similar situation. Now, what that means is we're going to have n ways, or I should rewrite this better yet using my binomial coefficient. I would have n choose 1 because of my n values, I'm going to choose 1 to be fixed. And that is the number that we are going to leverage and kind of work on to get ourselves out of here. Now, there is a slight problem with our process that we did here because it seems pretty straightforward. And that's why I did this on purpose. And I said this was going to be easy because we had to pick the fixed, and then we did this. But the problem with this is that if I picked, let's say here, I picked 1. So let's pick 1. And then I had 2 happen to go to 2. And then everything else is all mixed up. Well, that would be inside of here if I picked 1 as my first number. But if I picked 2 and I sent it to 2, and then I just happened to pick 1 and it went to 1, that would also be in here, which means I have just double counted the situation where both of them were in there. That's not good. So this is where the principle of inclusion exclusion that hopefully you learned comes back to play. So we're actually going to have to take away now, what if 2 of them, exactly 2 of them are fixed? We fixed 2, and then we kind of have to work from there. So actually, I'm going to erase this and move it over to the other part of here. So what I'm going to get is this. N choose 1 times n minus 1 factorial. But then I have to choose n choose 2 because I'm going to pick 2 of them to fix. And I'm going to have n minus 2 because once I fix 2, all the other numbers I can mix up. But again, that could be problematic because that could potentially allow us to still have 3. I could still have a situation. So then I have to add back in the 3 situation, which is n choose 3 times n minus 3 factorial. Are you starting to see a pattern here? But then I have to subtract again until I get the last one, which, by the way, would be n choose n times n minus, oh, it's going off the screen. Let me just put it on the next line. And I would keep going in this process until I get to this. But there's one thing missing. Notice that I have some of them being positive and some of them being negative. So all the odd ones are positive, all the others are negative. How do I deal with that in terms of this? Because I didn't really account for that. And this could, depending on what n is, this could be both positive or negative. So we actually have to throw in front of this a -1 to what power, mind you? And it's to the n plus 1. That way, if n is odd, it makes it an even number, makes it positive. N is even, that makes an odd number, which makes it a minus, and we're good. And this right here is the critical idea that we're going to kind of work on for this thing. So we're going to benefit from this. This, by the way, is going to be 0 factorial, which is 1. N choose n is 1. And so this is really just -1 to the n plus 1 is my final term. So that whole thing right here is really this. So we have a bunch of dots, and we can just write -1 to the n plus 1. So this is the principle of inclusion exclusion. This is why this is hard. The truth is, if you tried doing it the other way around, we took away how many are not fixed. The number of ways to do this not fixed. You're gonna hate me for this one. It's actually famous. If there's absolutely no fixed elements, it's a well-known mathematical concept called derangement. It's been studied a lot of ways. But that answer is, oh, sorry, undo that. Don't want that. It's going to be n factorial minus n choose 1 times n minus 1 factorial minus n choose 2 n minus 2 factorial plus oh sorry, this is a plus, this one's a minus. So notice it looks almost the exact same thing. The one thing difference again is that it's n minus 3 factorial. -1 to the n. So it's plus -1 to the n. So we have this. Now, this is why this is kind of a critical difference. Notice if I had taken n factorial from up here and subtracted this whole value right here, it would just give me our answer. So in reality, it's based on the same idea. How many ways are there? At least one. This is one of the more complicated ones, but sometimes I do generally recommend when students see at least one is ask the question of how easy is it to calculate the situations that I don't want? And if that's easier, then I would go down that path and simply look up things that way. All right. Hope that helps. Let me know what questions you have. Good luck. Go from there.